So, welcome to the first presentation in a two-part series on LaTeX that I have put together for PROSA, the Danish Union for IT Professionals. In this first presentation, we go through the basics of LaTeX, and we start by a motivation. So, why do we even care? And to do that, we start by looking at VisiVerg editors. So what you see is what you get editors like Microsoft Words and Google Docs. These are visual text editors that has a very low threshold for getting started. We have buttons for bold, we have shortcuts for bold, we have bullet points that we can, icons that we can click on and that we get those things. They also provide lots of distractions that compete for our attention. And that means that it's hard to stay focused on the task of writing. And that attention is key to writing well. At least for most people. And that also means that all of these small distractions, they slow down the writing process. They also provide very little help for managing references. They encourage bitmap graphics, which means that when we print it or show it on high-resolution screens, then usually it does not look very well. If it does look very well, then that's probably because we put in a very high-resolution image, and that ends up taking a lot of space. So the file gets big and chunky. Lastly, or next at least, the result tends to have very little consistency because we have the option, or we're always faced with the option of which font to use, which font size to use, how much space to have in between the paragraphs. We make choices. We make small choices here and there, and the result is a product that is not particularly consistent. Also, the formats of these editors, so a doc file or docx file or whatever a Google Doc gives us, those are fairly bad in terms of version control. So they're not really particularly Git compatible. Yes, modern formats are XML based, but those XML formats are huge and the specifications are huge, so we can't actually go in and reason about a merge conflict. These editors are also pretty bad for collaborative editing. They do offer it in a live version, and so that we can see where each author is in the document. But the moment we have more than a few authors and they are actually active writing in the document, it becomes very inconvenient because the text jumps up and down and yeah, bad experience. LaTeX, on the other hand, is essentially a programming language, and the source code is saved into a clear text file using some markup code. This makes it very suitable for version control, and the way I see it, version control is a form of collaborative editing. It's not live editing, but we do have, but if that is your thing, then there is stuff like, there are solutions like Overleaf that do exist and provide a similar experience to what you have in Word, or similar collaborative experience to what you have in Word. But what LaTeX mostly offers is a way of decoupling the structure and the presentation, or at least mostly offers this. And that gives us a very high consistency in our layouts. It also means that you don't have to care about the presentation of this. You don't have to care about which font is used and how to format all these different elements. There's a style, and that style provides us with that presentation level details, which also means that as a writer, it's very natural to focus on the writing and not the presentation. So the structure. But if you wish to, you can go into these details, you can change all of these things. Everything is parameters, and you can also overrule them. But mostly, there's no need. The default templates, they usually make things look great. So if you don't care, then LaTeX allows you to not care. It's also a highly extendable and mature system, so lots of tools exist. The tools are not necessarily as approachable as the graphical tools that you may be used to, but they do exist, and they have a lot of options that allows you to do basically what you want, more or less. And if you don't have the tools, then it's very easy to integrate with the existing tools, and you can write code by yourself that accomplishes what you want to accomplish instead of having to adapt. Working with bibliographies, that's trivial in LaTeX, as long as you know the basics. So is working with an index. So at the back of your document, an index where you can look up terms and which pages you can find those terms. Working with floats like figures and tables and referencing those, it's trivial. Working with equations is simple. I won't call it trivial because there's a lot to cover in order for that to be trivial. It's simple to get started with, and as you move along and needs to be something more complex, then it's also simple to incorporate these things one step at a time. References to any of these, so entries of the bibliography, figures, tables, sections, equations, there's probably a few I've missed, that sort of just works. It's also a professional typesetting system, and that means that everything is natively vector-based, so it scales very well. That doesn't mean that we can't include bitmapped graphics. That is also easy, but you sort of have to do that explicitly. So again, LaTeX is a programming language, and you write some source code that adheres to that standard, that syntax, that the semantics of that language, and when you evaluate it, it produces a PDF file. And you're probably used to programming languages that are based on functions or methods for logic that can be reused. In LaTeX, this is done through macro expansion, and that makes it at times a bit harder to reason about. But in the beginning, and for many people, this never changes. You don't need to know about how to write a macro. LaTeX has a fairly large number of packages. Currently there are 6,000 or more, actually more than 6,000 packages on C10, the Comprehensive Text Archive Network. There's a link here. And the next thing is that, as I mentioned, the contents and the presentation side of your document are mostly separate. The presentation side is defined through a style, and you pick your style. So there's a number of styles available to you, and those styles define how things look. It also depends. It also defines what structural parts are available to you, and these structural parts are. If you have a very large document, you probably have parts. Inside the parts you have chapters, then inside those you have sections, inside those you have subsections, sub-subsections, sub-sub-subsections, and somewhere in between all of these you have paragraphs, and so on and so forth. And these structural elements, or which ones are available to you without defining your own, that is defined by the styles. And how those are formatted is also defined by the styles. So which kind of margins, fonts, colors, spacing, that kind of stuff. Right now, this presentation is written in using a LaTeX package called Beamer. Usually, you would use LaTeX for documents like reports, articles, but you can also use it for presentations like this. You can use it for posters, and there are good reasons to use it for both. There are also good reasons to not use it. And we'll get to some of those in a minute. But should you be unhappy with the styling rules that are defined within the style you have chosen, you can pick another one, you can adjust it, or you can hard-code some specifics. There are options. But usually, you'll get something that is good enough. Maybe even better. And then, when should you not use LaTeX? Well, I used to use LaTeX for note-taking, because then I would know that I could always produce a PDF of it and print it out. And I knew that I would have all the different tools available to me so that I could easily express what I wanted to express in those notes. Nowadays, I don't do that anymore because I've realized that Markdown files are expressive enough and much faster to read, to write, and for that matter, read. Obviously, there's also separate note-taking tools that I also use, but at the current moment, I don't see much of a reason to choose LaTeX for note-taking. Then you have audience expectations. Often you have a target audience that don't really care about how things are, or don't care particularly well they don't care about how a document came to be. They don't care about, or often don't care a whole lot about how pretty it looks. What they care about is that they get a Word file that fits into the systems that they're going to use this in. And if that is the case, then you should use Word. I'm sure that there are some obscure program out there that can convert from LaTeX to Word, but it's just not worth it. Another reason to avoid LaTeX could be that you have collaborators that are not familiar with LaTeX, and then you should probably just follow the path of least resistance. So if your collaborator's skill set does not include LaTeX, then and you need to work with these, then you should probably use something else. Also, if the document you're producing is supposed to go on the interwebs, then you should probably use something that was originally intended with HTML production in mind. And again, you can convert LaTeX to HTML. From what the tools that I've seen for this do not produce particularly nice HTML output. And a lot of the positives that you gain from using LaTeX will be lost in that translation. You will still have the split between the content, the structure of the content, and how it's presented. But I would use something different, or I use something different when I produce, when I want to produce files for the internet. The second part is how we build this PDF file. And now that we do that by first producing a LaTeX document. We do that in your standard text editor, and then we need a LaTeX engine to compile that into PDF. And a few options exist here. PDF LaTeX is the old engine that has been used for quite a while. It is fast, but it does not support native Unicode. which also means that if you're using multiple languages of different with different alphabets that don't fit nicely into an ASCII variant, then this will get you into trouble. And for that reason, most people have switched to one of the next two options. We have C-LaTeX. There's a modern version of PDF LaTeX that fixes those downsides. It is slower and it's no longer actively developed, so I will skip that one. I'm using Lua LaTeX, which is the most modern engine. It also fixes the issues with PDF LaTeX, and it is under active development. It is, however, even slower than C-LaTeX. I don't see that as a big issue. It's not something that affects me a whole lot, though. Initially, I was drawn to the idea of being able to script this through Lua, but when I tried it out, it was quite cumbersome because the interactions between the Lua code and the LaTeX macro systems were fairly complex, and I didn't feel like reading up on how specific that worked. So Lua LaTeX, that's what I use for new projects. I'm converting some old projects to it, which is to say that I replace one command with a different command, and I'm not really changing the parameters to that command. It is simply the program name I change. So it is trivial. It is also Lua LaTeX that I will use for the examples in this presentation and in the examples of the report and presentation templates that I hand out at the end of this presentation. But you need more than the engine in order to work with LaTeX. You need a number of appropriate fonts, you need the engine, you need some packages, some selection of packages or extension. You need a number of support programs. And combined, all this is referred to as a LaTeX distribution. And there's, again, a number of those available to us. We have TechLive, which is the typical distribution, I want to say. It's available for Linux, Windows, and OS X. You have MikTeX that people usually use on Windows, and you have MacTeX for those of you on a Mac. When we have a LaTeX document, those, by the way, have the extension tech. So that could be called document.tech. Then we can compile it using Lua LaTeX with this command. For certain LaTeX packages, there's a need to call external programs during the build phase, and then you need to have the -shell escape flag on that Lua LaTeX command, or PDF LaTeX, or whatever engine you're using. This is, for instance, the case if you're using Minted for source code highlighting. Also, the way LaTeX works is that it does one pass of the document, and for multiple of the features that we're going to cover in this presentation, you need to run multiple passes, so you might need to run the command a few times. Now, there are rules behind this, so according to the rules, you can reason about how many times you need to run it. But if you're in doubt, then look at the last output of the command. If it says that some things are undefined and you need to run it again, then you run it again. But if you don't want to fiddle around with the command line, you can use an online tool called Overleaf. And this is the web page. You can sign up, you can sign in, and then you get something that looks a bit like this. On the left-hand side, you write your LaTeX code. On the right-hand side, you see a preview of what this would look like. And you can also download that file. Now, this is not a live update, but it's a close to live update of what is in the tech code here. The OLIF can be hosted in a number of ways. So they have free and a paid tier in the cloud. So they host that, and the paid tier provides Git support. I have personally had issues with uptime of their cloud solution. A few days before a big deadline, I've had students who have had similar issues. So I would prefer, I recommend doing the self-hosting. So basically there's a Docker file somewhere, a Docker Compose file that allows you to host this locally. You don't get Git support because it's basically the free tier version that you're running, but you're hosting it yourself, so you have the data yourself. If all else fails, you can just pull out the data. Personally, I am not really using OLIF anymore because of, well, the stability issues. Instead, I am putting everything in Git, using and treating my document as source code, and that works out very well. I use Make for building it. Make is a build system. I use it mostly because it's something that I know is very flexible and it is trivial to understand. Well, mostly trivial. I guess everything is trivial once you understand it, but, well, not everything. Anyways, up here we have some definitions. Here to here. Targets, that is essentially a list of files, this file and this file. Introduction, dependencies, again a list of files, only this one. Some other dependencies, this one, and this one. So I have one repository. This is actually the part of the make file that is used to build the presentation that I'm currently giving. And since that presentation is in a series of 2 that covers the introduction, an introduction to LaTeX, and an intermediate LaTeX presentation, then I have the introduction document, I have the intermediate document, and I have the dependencies for each of those. Now, the next part of the document, or this make file, is a set of target definitions. So let's take this one. The blue part here, that is the target itself. So this block here, these 2 lines, defines how to construct the ./fix/vector.pdf file, how to construct that file. And the construction recipe depends on this particular file. So basically we're building a PDF file based on the contents of an SVG file. And the way we do this is that we execute this command. We call a program called Inkscape, tell it to load this file, give it some flags, thereby telling it to load in the file, output it to this PDF file, and close down again. So here we have a recipe, again, for constructing this PDF file based on this SVG file by running this command. And what what make will do is that it will look at the timestamp of this PDF file and the timestamp of this SVG file, and based on that, it will determine if the vector.pdf file is up to date. If that is newer than the SVG file, then it's up to date. But this SVG file we could also have a rule for how to produce that. Then it would be on the left-hand side of the colon in some rule here. So here we have a text file that is produced by a Py file. So, and you can see that what happens here is that the Py file, that's a Python script, we run that script and it produces a text file. And then somewhere else we have a dependency for that. So by defining these rules, we essentially set up a dependency graph. And then you can tell Make, you want to build this file. It will analyze the dependency graph for when the different nodes of that graphs are up to date, or which nodes are up to date, which nodes are not up to date, and it will reproduce, or it will run the commands associated with those not up to date, so that it does the least amount of processing to make sure that your final document is up to date. Long description, you don't need to use Make. You can also, if you use Visual Studio Code or some other IDE with a plugin for LaTeX, it probably has a built functionality inside of that itself. However, that would probably also just allow you to build the LaTeX code. Using Make, I can call external code that will produce LaTeX code that I can then include. Or, as is in the case here, I have an SVG file that I can edit, and then it can automatically convert that to a PDF file that can be included. So, now that we have the LaTeX file, we have all the dependencies, we have the Make file, then we can place that in a Git repository. And that allows us to keep track of the revisions of these human readable files. I say human readable in the sense that the file themselves are human readable in a text editor. You don't have to use a graphical program to show you a visual interpretation of those files. So, again, it's a programming language. We can execute it to produce the PDF file, and that means that it should live somewhere in that repository. What I usually do is that I have a source directory in the repository for my program code. I have a doc directory for my report and presentations that relate to the code that I produced. And then I have some figures that I include in the report and the presentation under doc fix. In the templates that I'm going to hand out later, it's a bit more complicated, but that also allows for more flexibility and more reuse across these different the different reports and presentations. And that brings us to the basics. So now we've been through the first part of the presentation where it has all been a bit lofty because you haven't seen any code yet. In the basics, we go through that code, go through the code needed to do the basics. So a document looks like this. We have the document class. Here we're using the memoir style. We give it some options. We say that it's an A4 paper. We say that I think it defaults to letter, to US letter, which is a bit annoying if you are not in the US. We tell it to be one-sided. One-sided has a few implications. One of the major ones is that we have the same margins. It affects the margins. If it's double-sided, then the inner margins needs to be larger than the outer ones. Or that's usually the case, at least. There could be reasons not to do that, but let's not get into that. Then we have a block. We have a preamble. This is where we basically load the packages, and we also do some configuration of those packages and some parameters that apply to the whole document. Then we have this begin-end block, or environment as it's called in LaTeX speak, a document environment, and inside that we have three areas. We have the front matter, we have the back matter, the front matter, the main matter, and the back matter. We also call these segments. And I think technically it doesn't matter where you place things. but there are things that you would like to, that you normally place in front matter, things you normally place in back matter. So for instance, your table of contents, that goes into the front of the document, so that goes into the front matter. A bibliography, that goes into the back matter. And then your sections, or in case of a presentation, your slides go into the main matter. And throughout this presentation, I'm going to refer to the preamble, I'm going to refer to the front matter, the main matter, and the back matter. And this is what I mean by this. So first, we have the option of loading some packages. And a package is LaTeX terminology for a file or collection of files that contains a set of macros, so the commands and environments, that helps us deal with a specialized topic. For instance, there's a package called Dirty Talk. That is a very simple package. All it does is provide a single command called say, and this command takes one parameter. And what it does is that it wraps it in proper quotation marks. The quotations, a set of quotation marks that is a bit like a parenthesis, in the sense that it wraps something. And technically, we should not use the same typographical element before and after. So this here should not be the same as this, and say takes care of that. I don't need to be able to find these two on my keyboard. I can just use the say command for that. It helps me a bit when writing, but that's it. But in order to use this say command, we need to include this package, and we use the use package command for that. So that goes into the preamble. It's also a very simple package, only one command. When we include code, there's a number of packages for doing that. I'm going to present one called Minted, and in the next presentation I'm going to talk about ticks. Each of these are much larger packages with hundreds of commands, and that's simply because they're dealing with a more complex domain. Another thing we need to concern ourselves with is that when we write a document, then that document has to be expressed or produced in some language, maybe even more than one language. But we used to tell LaTeX, we use this line to tell LaTeX that our document will be in English. And we can change English for something else. It could be French, it could be Danish, it could be almost whatever. A lot of languages are supported, and most most LaTeX styles have a wide range of multilingual support. And this goes into, for instance, the table of contents. In Danish, that is indholdsfortegnelse. Sections that's spelled in a different way, same with figures, so on and so forth. So whenever you refer to something, there are parts of the style, so for instance the table of content, that you don't spell out yourself. You just say, I want a table of content. And since you have informed LaTeX that you want to do this in English, then it will write table of content. If you've informed it that you would like things to be in Danish and you insert a table of content, it will insert something that it will then choose to call indholdsfortegnelse, because that's the Danish version of that. On the side of that, LaTeX automatically breaks the lines, and it can choose to hyphenate words if it feels like this will help the final document look more pretty. So it has a lot of metrics for what it means for a document to look good, and it has quite a few parameters to adjust in order to accomplish that. So for instance, where it breaks the lines. If you have a line with lots of long words, then it might, and it doesn't break the word, then it might need to expand the spacing in between words quite a lot, and that doesn't look particularly well. So it will try to break the words where it sees that this can result in a better looking result. But not all words are in its dictionary, so it doesn't necessarily know where to break all words. So if you find a word that you're using that is not in the dictionary, then you can add that specifically. And that's what we do in this line. Here we add two words, and we use dashes to inform LaTeX of where it is allowed to break that word. So algorithms can be broken here and here. Mechanics can be broken here and here. So if you see that there's a word it doesn't break properly, you add a rule like this. And in order to structure our document, you can do a LaTeX report in a single file. I have done that. I've also done that fairly successfully. It's not necessarily a problem, but as programmers, or most programmers who has experience with larger pieces of code, has an understanding of the problems that can stem from having all our code in a single file. So LaTeX, like almost any other language, has a construct for addressing code that is in a different file. So by using the input command like this, LaTeX will take the content of filename.tex and essentially insert it here. Here being the location in the file where you have this command. So that way you can have, say, top level sections in individual files, you can have figures in individual files. There's a reason to have, where you might have figures in one file per figure, and that is that if you have one repository for both your report and a presentation about the same topic, then if you have your figures in a specific file, or in one file per figure, then you can simply refer to that file from both the report and the presentation. And that makes it trivial to reuse figures across both. However, while we may have a good understanding of the problems that comes from having all code in one file, it seems quite common for people or programmers to not understand the problems that comes from having our code split across a large number of files. So use this with care. Don't split it up too much. What I would do is that I start on one file, and then when things get a bit too unwieldy, then I start pulling it out into smaller files. Basically refactoring the code. Our document, I mentioned this a bit earlier, this depends on the style. We may have access to a part, so our document can be split into part 1, part 2, part 3. Underneath we have the chapters, underneath we have the sections, under these we have subsections, and this kind of structure goes into a tree. This is a tree structure of our document. And as leaves on that tree, we have paragraphs. And again, which levels of this structure are available to you depends on the style. But it's going to look a bit like this. So we have a part, and because this is the first part, this is part 1. And we call it reasoning. underneath that we have a chapter called Introduction that has 2 paragraphs. It has 2 paragraphs because there's a blank line in between. Then we have a new section. Well, we have the first section called Problem. We also have a section called Approach that is at the same level as Problem and both under the Introduction chapter. We have a new chapter called Analysis. We have a section under that called Themes. Under that section we have a subsection called Build Systems and one called Scripting. And then we go to a section, though that must be at the same level as Themes, called Subconclusion. And this goes into the main matter. I mentioned this command thing, and I also briefly mentioned an environment. A command is something that looks like this: a backslash, then a name, and then 0 or more parameters or arguments in curly braces. That is a command. An environment is something that is wrapped within a begin-end. So this is a center environment, and it takes whatever is in between and, well, centers it. So we have commands, we have environments, and all of these we can nest in different ways in order to compose our code. And like so many other programming languages, then whitespaces are treated in such a way that either you have no whitespace or you have at least one. So these are the 2 cases: none or at least one. If there's at least one, then a space is inserted. So the amount of spacing that is inserted does not depend on the number of spaces. Either we have a space or we don't. And this also means that you don't really have to concern yourself whether you accidentally added 2 spaces after a period that is going to cancel out. And LaTeX does this thing where it has all these scores for how bad the layout of a document is, and tries to optimize the layout of the document by minimizing this badness concept of score. That also means that it can be hard to place something at a very specific location. At the next presentation, I'm going to talk about how this can be done with ticks, or at least how we can place things at a specific location relative to the page. But this thing about it automatically trying to optimize the layout, that also gives us, or can give us some anxiety in the beginning. So often people start by essentially building the skeleton of the document. So we have these chapters, we have these sections, we have these subsections, and then starting to fill in, the main figures so that you have something to write about. But if you do it that way, which I also do, but when you do it that way, then a lot of the rules that go into the layout of the document will be playing against you. So, for instance, LaTeX will try its best not to have a section title at the end of a page, because it just looks bad. It should be on the same page as the following paragraph. So if you haven't put in any paragraphs, it's having a very tough job laying out stuff. Which also means that it might end up putting your figures very far away from where you think you put them. But my suggestion there is that you wait it out. Once you start to add in the text of the document, the ability for LaTeX to place things in reasonable locations improve and improve and improve. And usually it's all fine at the end. The moment you start to overwrite things, hardcode things, then you're essentially tying the hand of LaTeX behind its back, and you will make it harder for it to do its job. We can put in horizontal and vertical spaces using the H space, horizontal space, and V space, vertical space commands, and they take a parameter, a distance. So the H space looks like this, and you're going to see slides that looks a lot like this throughout this presentation. On the left hand side you have LaTeX code, on the right hand side you have what it looks like when LaTeX has been through that code. And you can also see this in the source code for this presentation, which will be linked at the end of the presentation. So this means that there's a centimeter in between here, or at least that would be the case if this was printed on paper, but when it's a presentation viewed on a screen, then it's not necessarily 1 centimeter, but it would be double the distance of something that was 5 millimeters. We can also have a V space, so vertical space. Now there's 1 centimeter in between here, maybe plus a paragraph break. We can switch the font, say that now I want something here that is bold. I can use the slanted font, I can use an italics font, and because LaTeX, and now that this is a presentation, we're not necessarily seeing all the fonts available to us. Some of these font styles are mapped to the same actual font when we're doing presentations. That is not the usually, at least according to the style, not the case when we are targeting a report or article that is supposed to go on paper. So what here? Teletype, that is constant width. Serifs free, that is a font without serifs. Slanting and italics are very close to each other, also on print. I usually prefer slanted because it is a variant of the standard font, whereas italics is a completely different font. Looks similar, but it's a different font. We can have different font sizes, and the font sizes are named and relative. I say that they're named because usually we don't, so we say something, this is a normal size font, that's the default. We don't say this is 11 points. I think there are mechanisms for us to actually say that this needs to be this font size, but normally it doesn't make sense. And the reason for it not to make sense is that the differences in size between two of these is reasonable. It is something that a reader will notice. That's not necessarily the same between, let's say, a 24 and a 25 point font, but these different sizes has been laid out relative to each other in such a way that it is noticeable, but not too much, the difference. And in the slide we saw earlier, summarizing the whole document where we had parameters for the style, we can also say normal size needs to be this size, and thereby essentially shifting this whole scale of font sizes. We can have listings, and so these are basically these are your bullet points or your ordered, unordered lists. And generally, when you pick between these two, so enumerated, here you enumerate the bullets. Itemize, here's just bullets. When you pick between those two, you should consider, have you in the text around that listing mentioned the number of items? If that is the case, you should probably consider using an enumerate environment and thereby number the items so that the last item will be the same as the number. If that is not the case, then consider, do you have a need to refer to a specific item? If you have that, then that item needs a number. So you can say, please look at item number 7. You can't say, please look at item with a bullet point if all items have a bullet point. And if none of those are the case, you might as well just use bullets. If you want to use bullets, then this is how you do it. Here we have a list of programming languages, we have an itemized environment, and then we have a number of items. These are commands. Because I'm using the default template of Beamer for presentations, then that style will essentially convert an item to a blue triangle. If you use a different style, it will look differently, and you can overwrite this if you want to. Anyways, programming languages, Rust, Elixir, Python, LaTeX. Now, if we want this to be numbered, we use an enumerate, simply by flipping the environment from itemized to enumerate, and it will just work. Nice. But let's say that we have something that is enumerated, and we want to refer to one of those numbers. We can do that, just as we can refer to the number of a section, the number of a figure, a table, equation, and the way we do that is different from the way that we work with the entries of a bibliography. We'll get to that later, but right now we just want to refer to a figure, or, well, in the example that comes up, it is an item of a numbered list. And we use a label to essentially put in an anchor point. And that label goes in somewhere in our source code. And the last thing before that label that was enumerable, that is the thing we're going to refer to. And once we have that anchor in there, we can refer to the number using the ref command. We can also refer to the page containing that anchor using the pageref command. And because of the way LaTeX works, it does one pass, we need to run LaTeX at least twice to make this work. The first pass that will note down the positions of the labels and what those labels, the number those labels represent, and the page on which those labels are. And the second pass will insert those things at the positions where we have the ref and the pageref command. So let's see an example of this. We have an algorithm, and we want to first initialize, then we do stuff, and then we go to step number 2 here. So what does this look in LaTeX? Well, we have our enumerate environment. It's an enumerate because we need the numbers here. 1, 2, 3. That is done automatically. And then we have a label, ID, we call this place. And that label refers to this item, and this item has number 1, 2. So ID refers to this item, so when we reference that, it will insert a 2 here. And one thing that I often see done, in my opinion, wrongly, is that people forget this word, step. So it's just write go to 2, which is not technically wrong, and it's not that big of a problem here. But if you say see 2.3 in a text, then the reader will not know if 2.3 refers to a section or a figure or a table or whatever. So try to always put in this qualifier. Is it a step? Is it a figure? Is it a section or whatever? That makes it easier for the reader. We can also use colors, and there's a few different methods for this. So we should in our preamble put in this command to include the package color. Then we can define our own colors this way. So we give this color a name, my favorite color. We choose a color scheme, RGB in this case. RGB is the most common way to use colors in a computer. And here we essentially give it 4 double values of floating point values between 0 and 1. The first one represents a red component, the next one a green component, and the last one a blue component. I believe it also supports HFSV and a few of these other color schemes, HSL, so on. Now that we have defined that color, we can use it down here. And we can also use some other of the predefined colors, for instance, purple. And the predefined colors we can see down here. We're going to go to that in a moment. We can also mix already declared colors. So here we take the red color and then we keep 27% of that, and then we add in some green. I think that's how to interpret that, but you can try it out. And it will look like this. LaTeX has a fairly large number of predefined color names. And let's try to go to this website that lists them. So here we have almond here, and it is this definition that is at play. You can always use all, and those names, so not those names here because they have spaces, they have they have some capitalization. Use the names that are in here. And you can scroll through this if you just want to look up a nice color. And the colors here are generally nice because nobody wants to give a name to a horrible color. So these are usually colors that might fit in well in a document. The next step is presenting tabular data. So tabular data, those are data that you would normally see in a table or a spreadsheet. And let's just limit ourselves to 2 dimensions here. So we use the tabular environment for that. And this does not contain anything, but there are 2 areas here. We have an area up here where we have a format definition, and we have an area down here where we put in the data that then is laid out according to that format definition. The format definition specifies how to arrange data in cells. So essentially, for every row, we take the cells of that row and format them according to that specification. And the specification also has, through that specification, you can also define where you want vertical lines, so between which cells. So a bar, that's a vertical bar line. L, we use that to define that a cell needs to be left justified. C, cell needs to be centered, right justified. And then we have a paragraph that is 5 centimeters wide. That means that LaTeX will automatically break the lines within that cell and make sure that this column is only 5 centimeters wide. The data itself, there's 2 types of lines we can put in there in that segment of our tabular environment. One is that we can put in H-lines. An H-line is a horizontal line, and the other is that we can put in data that has the same format as our data format definition in the previous slide here. Let's go forward again. So each of these lines that are used to place data, they have cells separated by an ampersand here. Each of these rows needs to be terminated by a manual line break, and that is 2 backslashes in a row. There are ways of merging cells, both horizontally and vertically, and there are ways of defining a cell color. I'm not going to go into details about this, but if you care, then you should look up the multi-row, multi-col, cell color in combination with LaTeX tabular environment. Then you're going to find plenty of links that cover these things. Here's an example. We have a tabular environment. We have a left bar, so a vertical line at the left of the table. Then we have a column that is left justified and 2 columns that are right justified, and then a line again. And then inside of that we have a horizontal line at the top. Actually, we have a header that is separated by horizontal lines. Then we have some data, and we have a new horizontal line. And the header here has the column names country, area in square kilometers, and population, and all of those are in bold. And then we have, for data, we have the area and the population of Denmark, Greece, and Finland. And when we build that, we get this table. And this can get much, much more fancy, but you get the idea, the base idea at least. The next thing we're going to look into is how to put in visuals. And LaTeX supports a number of types here. And we can categorize them a bit. We can categorize different formats according to whether they support bitmap graphics, whether we can actually include them in LaTeX, whether they are lossy, which we would prefer them not to be, whether they are vector-based, which means that we can keep on zooming into them without things getting pixelated. We like that. And whether they are native to LaTeX. And the first one is JPEG, which naturally is bitmap. We can include it, but it's lossy. So I think there might be options of compressing JPEG files in a non-lossy way, or lossless way, as it's called. But most JPEG files are lossy, and that means that they include compression artifacts that will look pretty horrible when printed. PNG, essentially the same as JPEG, but it's lossless, so I prefer that always. SVG, it is vector-based, but it's not something like we can include directly in LaTeX, unfortunately. There's PDF, which is like SVG, but we can include it. And then we can actually convert SVG to PDF, so indirectly we can conclude that. We can include that. That's the right term. On top of that, we have something called TIX, which is a pretty large LaTeX package, and there's lots of extensions to it, and it is I'm not sure if I want to call it a convenient, but it's a powerful way of creating graphs of very different sorts. And at the next presentation, I'm going to dig a bit into that. Just scrape the surface. If we have some PDF file and we want to include it, we can use this command. We can say that this is the file I want to include. I want it to be 45 millimeters wide. And it's going to appear like this. Now, this slide does not have a white background. It has a slightly bluish background. This file here has a circle, and then it has, I think it's a Bézier curve here, and a line here. Which means that this area here, the area here, and the area here, those are transparent. They could have been filled, then they would probably have a different color, the fill color. But here they're not. But that particular file here, that was not originally a PDF file. If you recall the make file at the beginning of this presentation, then that make file had a target called vector.pdf. So let's take a look at that. The original file for this, that was an SVG file that I created using a program called Inkscape. It's freely available, it's open source, and while it operates at a fairly low level of abstraction, it is pretty good. Inkscape can save SVG files. It can save, I think it can also save PDF files. But if you work with it, you probably want to save as SVG because that is its native format. There are lots of other programs that can export and save work with SVG files. This is just one of them that I happen to use. We have no native process of including SVG files in LaTeX, but using this command, I can convert this SVG file to this PDF file. And that particular line is stolen from the build systems for this presentation. So, if we look at the SVG file in its entirety, it looks like this. We have a header up here, then we have the outermost tag SVG that contains a lot of metadata about this and some definitions that are not particularly important for the contents of the file. Then the content itself is in here. We have the ellipsis here, that is our circle, which if we look at it is not completely circular. We have two radiuses, the X and the Y, and because they're not the same, they're not technically a circle. Then we have a path here that is, I think this is our Bézier, and then we have another path here, and that's it. And because things here are defined in terms of vector operations, circles, lines, paths, that again are defined using points or reference points. Because of that, we can zoom into this indefinitely. And yet, it fills up almost nothing on our disk. But not all things we want to include are things that fit well into a vector format. Some things are inherently bitmapped. Photos, for instance. So this is an example. This could have been a JPEG, but it happens to be a PNG, and it has a specific width, or I tell LaTeX that please load this image and scale it so that it has a width of 45 millimeters. It will conserve the aspect ratio then. I could also tell it to have a height of something, and I think I could also tell it to do both, and then it would break the aspect ratio if need be. Yeah. Those bitmapped images, those PDFs or SVG files, including here, they would just be included where we place the code. And that is rarely what we want when we're writing a report or an article. So you should expect your reader to follow the main track of the text from top to bottom. So it should be possible to read that text from the beginning to the end without being forced to look at figures and stuff like that. So we still want to be able to refer to these figures inside of the text, but we want it to be up to the reader to choose to look at those figures or not. So it shouldn't break the flow of the text. So how we do this is that we make sure that the text flows around those figures. We make sure that the figures are somewhere close by, they're easily located, and they're referred to by a figure ID, figure 7 for instance. That way they don't break the flow, and we say that they float. You know this from figures and you know this from tables. Here we have an example of a figure, and you can put in some content here at this instead of this comment. So typically you would have the inclusion of a PDF file here or a bitmap file, but it could also be just some text or a table. You give the figure a caption, you give it a label. That means you can later on refer to it just as we refer to one of those bullet points in the Enumerate environment. And we also have tables that looks like this. That is exactly the same, except for a slightly different caption, a slightly different label. You just put in your table here. The main difference is that this is a table environment and not a figure environment. Now, figures are numbered from 1 and onwards. Maybe maybe the numbers reset within a section, but they're essentially numbered continuously. And the same for tables. Now, personally, I'm not a big fan of this, because what I want is, given where I am, I want the first cue that I can find in order to figure out, do I need to turn the page forward or backwards in order to find the figure I'm looking for or the table I'm looking for. And if they are on different numbering schemes, then I need to find something of the right numbering scheme in order to know which way to look. So personally, I often put both tables and figures inside figure environments, because in my mind a table is also a figure, but a figure is not a table. So I use figures for everything. But this is one of those things where you will find people who agrees and people who disagrees. If we look at the figure again, so this is exactly the same code as before, then we have this area, TBP. Those are not random letters. In fact, they are instructions for LaTeX on how to position this code, or this figure, and where it's allowed to position it. T means that it's allowed to be positioned at the top of a page. B means that it's allowed to be positioned at the bottom of a page. P means that it's allowed to be positioned on a page that has nothing but floats. So a page that doesn't have any text outside of at least not outside of figures and tables and what else there might be float-wise. And when I say what else there might be, that's because I myself have, or you can create your own floats. So if you so we have, I think you have access to, by default you have access to tables, figures, code listings maybe. So code listing 7, something like that. But you can also create other stuff, and I've done that myself. I think I will talk about that in the next presentation. You can also use H, which essentially stands for here, or approximately here. That instructs LaTeX to try to place it where it's been placed in the code. And that's going to compromise a bit on the badness of the layout. So this thing that it tries to optimize. And if you put an exclamation mark after the H, then you're going to override some of the parameters that LaTeX uses to determine what it means for something to be a good position. That essentially means that you insist that it needs to be here. And because of that, so these two instructions down here, the H and the exclamation mark, they essentially put LaTeX at a disadvantage. Tell it to work under worse conditions. So usually you should avoid those two. And if you don't, then at least wait until you have written most of the document before you start adding them, because again, the more text you add, the easier it is for LaTeX to do something reasonable with, for instance, the TBP that I usually use. Then when just before you hand in, you can put in your H and your exclamation mark if you're not happy about the result. We have footnotes. So we just write footnote and then whatever we want to go into the footnote, and it will look like this. It looks a bit weird that it puts in an A here. That's because this is a presentation. Had this been something that was charged in paper, that would probably have been a 1. On a similar note, we have something called margin notes, or margin paragraphs. And they're more or less the same as footnotes, except they go in the margin instead of the footer, and they're not numbered. It's just text going into the margin. And it looks like this. Credit Isaac Newton. We can include code. And there's a lot of different implementations of this. I am going to go through Minted. Minted supports a pretty long list of file formats. File formats / programming languages, depending on what you want. And actually it also supports shell interaction, so that it will highlight your prompt in one way, your command in another way, and the printout in a third way. Something like that. It also supports all kinds of highlights. So if you want to highlight certain lines, if you want to number your lines, if you only want to show a part of the code, there's lots of options here. And you can essentially do this, include code in 2 different ways. 3 ways really, but let's say 2 different ways for now. One is inline, where you have your block text. So this is a paragraph. Your paragraph starts up here and ends down here. So here we're saying that the formatting of a function call in Rust looks like this. Fun, parenthesis, 1 + 1. And we tell Minted that this is an inline. So it shouldn't break the line here. And it should format this parameter as if it was Rust code. And if we look over here, we can see 1 + 1, at least if you squint your eyes, that's a bit grayer than the rest of the text. That's because the formatting rule states that expressions needs to be highlighted like this. And all of this thing about what needs to be highlighted how, that is part of a theme that you can configure for Minted. But I'm not going into details with that, because often you just care about it being highlighted instead of not highlighted. The other way of including things is to do it as an environment. And here we have an environment that is being highlighted as if it was Elixir code. And then you can see that there's a module called enum that is being highlighted. We have an anonymous function that is highlighted here. And that's it. We also have the option of referring to a file and say, I would like the content of that file to be highlighted as if it was this kind of code. I don't think I have an example for that. No, not here. But later on, I will link to the templates that I hand out for writing reports and presentations, and in that there's an example of how we do this. Then we come to mathematics. This is one of the things that LaTeX is well known for. Typesetting mathematical expressions. And at first that can seem quite daunting because there's a lot of syntax and code for different constructs, and well, the number of constructs is very large, so where do you begin? But there's a system behind the madness, and when you start out, you're probably going to need a very, very small subset of this. And then as you go on, maybe now and then you expand it a bit. And it's not that hard to remember. For instance, if you want a fraction, then a fraction is something you implement using the frac command. It takes two parameters, a numerator and a denominator. And when you think about what is a fraction, it is a numerator and a denominator. So it makes a lot of sense. At the same time, square root, that's called square root, like it is in most programming languages. So, and like the code inclusion, again, mathematics can be done inline or in an environment. So let's take a look at those two options. Oh yeah, before we do that, the codes for Greek letters are named after the Greek letters, and we have a large number of weird symbols. Do an image search and you will find tables of those symbols and the corresponding LaTeX commands. But inline, again, one paragraph starts up here, goes to down here. And then we switch from text mode into mathematics mode and out again by wrapping the mathematics in $signs. So this is in math mode and this is in math mode. And it renders like this. And again, it looks better if this was intended for papers or in a report or an article. We also have the environment version that looks like this, and it's a bit larger because we have this left-right arrow, that is this one. We break the line so that we can have the other equation here, and the environment is called align because it aligns the ampersands. So it makes sure that those two are on top of each other, which ends up meaning that the equal signs are on top of each other here. That's just a way of making it look pretty. The asterisk here means that each of these lines, it means that these lines are not numbered. If we want them to be numbered, we remove that asterisk and we get the 1 and the 2. These can be labeled, in this case pith 1 and pith 2, and then we can refer to these references as equations. So this can be expressed as either of equations 1 or 2. References to these. And now you've seen how we raise some text, that is with the hat character here. We can also lower text with an underscore. So H2O looks like that. The hat and the underscore affects the next character. So the 2, not the O, and the 2 here. If we want H underscore 20, or then we will have H underscore, and then we need to group those characters using curly braces. URLs. Well, the low-tech version of this is that we probably want to print them as teletype, so constant with font, because that's how you normally think about it. And then you can call it blue. It will look like that, but then it's just text. We also have a URL command, and that will make it clickable. But it won't call it blue, so I might combine the two. I also have an href whereby I insert the text of the second parameter and make it clickable to the target of the first parameter. So again, I can click this. I can also make that blue if I want to. And then we have a few details from here and there. You may have seen me using the LDots commands. That is in order to produce 3 dots in a row. That will look differently and prettier than just having 3 periods. However, commands like this, at least those that don't have a parameter, they will eat the following spaces. So in order to avoid that, you can put a backslash after that to escape that space that comes here. And that's what I've done here. If it looks weird, look into the source code for this presentation and you will see how I accomplish that. It's very simple, you just need to know it. The same goes for the LaTeX command. If you want to center something, we have the center environment that we covered earlier. We also have a centering command, and they are very similar. The centering environment adds a bit of spacing, but it's easier to work with than the centering command. Yeah, I think that's it. Part 4, auto-generated lists. So far it has been mostly static contents. The references has not been, but mostly static. And that's not the case for the table of contents. The table of contents is going to be built automatically based on which parts, chapters, sections, subsections, and so on that you have. But if you have a large document with lots of section and depth, then you can easily end up with 10 pages of table of contents, and maybe that's not what you want. Maybe you just need the parts, the sections, the parts, the chapters, and the sections in there, and you don't care about having the subsections and the subsections in your table of contents. And if that is the case, then you can restrict the section depth to, for instance, 2 by putting this command inside of your preamble. Or maybe it's the front matter. Anyways, it's up there somewhere. If it complains, then it's probably in the wrong location. Also, there's some default for this. Maybe the default is infinite, I don't remember. It probably also depends on the style. At one point we want to place the table of contents. We do that using the table of contents command. Doesn't take any parameters. And the location where we do that, that is the location where it places the table of contents. So that usually goes at the top of the document. Oh, all of this goes into the front matter. So it doesn't go into this doesn't go into the preamble, it's the front matter. Note to self. Similarly, we have a list of figures, we have a list of tables, and we can insert them by putting in this command or this command. And again, the list will be inserted at the point in the document where we have this command. Bibliography. So now we're going a bit away from LaTeX and more into report writing. When we write, we need to give and take credit for the individual parts that make up our work. So this has 2 components. One is that we build on what others have accomplished. And in doing so, we need to give them credit for that work. But we also come up with new insights, and we need to take credit for those insights. The way we give credit is that we cite it. And LaTeX has a fairly extensive framework for doing this. So when we look up work on the internet, and as we discuss in LaTeX, then most of you will be working with software. That means that most of the articles that you're going to find are going to be on ACM or IEEE, And this is an example of such an article from ACM, which means that it has a page on ACM. The article has a page on ACM, and you can see the title of the article, you can see the authors, where it was published, when it was published, how many citations it has, and some other number of things. You can also see a quotation mark here, and when my mouse hovers there, it pops up a text called Export Citation. When I click there, it gives me some options, and it defaults to BibTeX, which is exactly what I want. So I copy the code in here, and then I paste it into a separate file, and it looks like this. Again, this is highlighted using Mended, and because it knows what a BibTeX file is and how that should be formatted. I've also instructed it to break the lines, and when it does that, it inserts this funny character to show that this line has been broken. But what you see here is that it is a bibliography entry, and there's a number of data points that are relating to that. You have a list of authors, you have a title, you have when it was published, you have an ISBN number, who the publisher is, a URL, lots of stuff. And it also has this thing. That is the ID. Right here it is in digits, it is periods, it is slashes, but it doesn't need to be. It could be my awesome document. It is just an ID. Also, this is one entry in one file. That file could have multiple entries. And if we store that file in references.bib and put this in our preamble, so basically we're going to use the BibLaTeX package, and we're using the Biber backend, and we're adding the resource references.bib. That is the file we saw in the previous slide. Once we have done that, in our text, we can have some statement, and then we can put in a side this ID. That was the ID of the document, or of the reference. And that's all we need to do. Well, almost all. We also need to put in our back matter a print bibliography line, just like we had for including the list of figures and the table of contents. And once we have this, we can run LaTeX, not once. We can run LaTeX once. It's going to see that we need to include this entry from our references.bib. It's going to see that and put it into like a temporary file. Sorry, this is what happens when we run Biber. Anyways, there's a number of commands that needs to be run, and any execution of LaTeX or Lua LaTeX after that will automatically produce what needs to be inserted here and make sure that the reference inserted here links correctly to what is being inserted here. We can also do indexes, and in short, an index is something that allows us to look up a term and see and get a set of pages that are relevant for that term. It usually goes at the back of a book, and at least at the back of a paper book, and I have the feeling that nowadays it's sort of going away, but it is very convenient to have, but usually in reports we don't use them. But anyways, we can go in and we can tag something, a position for inclusion. So if I go in and say index term, then at the position of this piece of code in the document, that will be, it will look up the page of that position and add that page to the index onto this term. And then, again, somewhere in the back matter, I print the index and that appears there. And again, this is a two-pass thing. So first we'll run LaTeX once, then we run the make index command here in order to do the indexing stuff, and then we run it again. LaTeX again. Part 5, errors. So errors in LaTeX are harder to reason about than errors in most other programming languages. Often the line number does not reflect the actual line in the source code, which is really annoying. One of the reasons for this is that the source code are macros inside of macros inside of macros inside of macros. And especially if you look at the commands, then the command has parameters that are wrapped in these curly braces. And if you miss one of those, then that command sort of never ends. And you're just going to hit the last line of the file, or the last line of a wrapping environment. And then that is the line being reported. Quite annoying, but you sort of learn how to deal with that. Because of this, I frequently build the document so that when the build fails, I know that since the last time I built it, I really only touched 5 lines. So I've probably done something wrong in those 5 lines. Another thing I do is that when I get a larger error, something where I haven't actually built it in, say, a few days, and I've written quite a few lines of code, maybe I've done larger changes to the code base, moved stuff around, then it's hard for me to reason about where the problem is. In that case, I essentially do binary search in order to determine where the offending part of the code is. And I do that by commenting out, say, the first half. I bisect the code, comment out the first half, see, does it compile now? If it does compile, then the offending line was in the first half of the code, and then I can split that into 2 halves, and through that way I can narrow down where the problem is quite fast. Many of these errors we have are easily Googleable, and when we Google them, we will find hits on sites like Stack Overflow, just like pretty much any other language. But in order to get to improve your way of Googling these errors, you need to consider what you paste in. LaTeX errors have a tendency to be quite verbose, and if you paste everything in, then the search engine is going to have a hard time figuring out which parts to focus on, and it's probably going to focus on something that is irrelevant. You should also consider what type of error it is and look up that type of error, figure out what could cause that type of error, and whether these conditions apply to your situation. Don't be afraid to take one extra step down the rabbit hole. Of course, that will take some time, but this is time you invest in building up your skills in order to deal with this kind of problems. And I would even argue that this is transferable beyond LaTeX. Part 6, resources. So on Wikibooks, we have a LaTeX book that is actually quite large. I would guess that 80, maybe 90% of what I've covered today, you can find there. You can also find 50 times as much information. There's a lot of stuff in there. When you Google a specific problem, you're likely to end up either there or on Overleaf Learn. So Overleaf, that was this online LaTeX editor, and they have some documentation that is also pretty good. You have generators for tables and equations on the web, so that you don't need. So in the beginning, when you're not that comfortable laying out a table writing an equation in LaTeX, you can get the help of these. And maybe even later on, if there's something very specific that you want from your table or your equation. But after a bit of time, you're probably going to want to write things in hand because it's just faster and more convenient as a work process. You also have ticks, again, that I'm going to cover in the next presentation. This is for graphics, vector graphics, and in particular graphs or variations over graphs. If you want to include a list of abbreviations or glossary, then I can recommend this link. The source code for these slides can be found here on Git, and I have created templates for producing reports and producing presentations, and they can be found here. In a minute we're going to there, and I'll give you a short introduction to the structure of that. I plan on placing all of this material on this URL. It's not there now, but it will be at one point. This was the presentation. I have prepared a few exercises for you to get accustomed with this. The first one is create a new project, whether it be on Overleaf or GitHub or similar, or just local in your file system, it doesn't really matter. Make a LaTeX report that builds. And for now it can be empty. Just make sure you have something that builds. Then another exercise that sort of depends on the first one is that go out, find some tabular data that you find interesting, place it in a tabular environment, and make it look pretty. So what kind of columns how do you want to organize the columns? Do you want it to have a background color? Do you want something to be bold? Where do you want which borders of do you want to highlight? Do you want cells do you want to merge cells? That kind of stuff. And then you have a similar exercise again that sort of depends on number one, where you pick any formula and you express that through LaTeX code so that you can build that into a PDF. And if you don't have a particular formula that you find interesting, then go look up the formula for the discrete Fourier transform. You can find it on Wikipedia. You can probably also just Google it and go to images. And I think this is the last one, and perhaps most important one. Again, that depends on number one, but not number two and number three, at least not necessarily. You pick any old report that you've written and you port it to LaTeX. And that might sound like a huge undertaking, but take it with a grain of salt. It's not the purpose of this is not to port it to LaTeX. The purpose is to get some experience with the process of producing LaTeX code that makes it into a PDF. So start from the beginning and port a few sections. Not necessarily the whole thing. We don't care about that. We want you to get an idea about the effort needed to write LaTeX code or to port LaTeX code, to port an old report into LaTeX. And we want you to have an idea about how that effort translates into the perceived typographical quality of that result. This will give you an idea about the trade-offs of choosing LaTeX over, say, Google Docs or online Word or whatever. So the moment that you feel like you have that feeling, you're done with the exercise. Good. Then let's go to the GitHub repository of the LaTeX templates that I linked to at the end of the presentation. And there's a README file here, and there are two things I would like to point out. One thing is, well, if I go to the doc file here, then we have a make file here, doc directory, we have a make file, and we have the target for the report, target for a presentation, target for handout. They each refer to a LaTeX engine that is defined up here. But if I go back here, so if you're on a Unix box, or at least a Linux box, and you have the right dependencies, that is going to work. You just go in there and you write make, and it does everything. But if you don't have your dependencies lined up, then you either need to get them lined up, and that's going to be very hard if you're, say, on a Windows system, but you can also use Docker to build it. First, you build the image using this command. Then, once you want to, then as part of your work process, every time you want to build it, you run this command, and that essentially says this template, the image that we created up here, inside of that, run the make command. And you can put in any other command that you want to run here. And if you have multiple projects where you do this, you probably want to give them different names. So it shouldn't be called LaTeX template, maybe it should be called semester project report, something like that. So using Docker, you can build this without having to install all the dependencies locally. Then there's an overview of the repository structure here. And we have the make file. Then we have a BibTeX reference, some references for BibTeX. We have some metadata. So if I click here, you will see that there's a title and there's an author. That's it. That goes into both the report and the presentations. Then we have some shared code. These are inclusions of packages. It is definitions of convenient commands. Then we have a main report file. And the main report file, if I go down here, it includes a number of other files. Let's go back. Those other files are in here, in that directory. In the same way, we have a file for the structure of the presentation, and that refers to documents inside of slides. But because the output of this is PDF, we want to produce the slides in two different formats. The presentation format and a handout format. So the difference between those two is that you may have a slide where you reveal part of the material of the slide through transitions. So if you have a slide where first you show the first half and then you want to show both halves, then if we build this as a presentation, that will result in two slides, two pages, so to speak, in the PDF file. But if you do that all the time and you have slides with 5 or 15 transitions, then that's going to end up being 5 or 15 pages. And that is horrible to hand out to people. So in the handout version, those are collapsed. Now, if I click on the handout version here, then it uses the Beamer class and input some shared code. Then there's something about removing a footer and basically include the slides file. Now, this is exactly the same as the LaTeX file for the presentation, except that this one also has the layout option, the handout option. And both use the 16:9 aspect ratio. So, where are we? Yes, material. We have a material folder or directory. Inside of that we have a source directory and a generated directory. Generated means that these files are auto-generated. So at any point you can remove these files, and the next time you try to build it, they will be recreated. And they will often be recreated from what is in the source directory here. Inside of the slide files or the report files, we can refer to what is in the source and the generation directories here. So we can have material that is shared across both. And I think that was what I wanted to show today. So thanks for watching, and I will record the next presentation as well.